Okay, the next talk is by Professor Vladimir Anashin. Title of the talk: Causality and Time, an Ultrametric View.
Okay. First of all, I would like to thank organizers for this, for the possibility to organize this conference online. It's also okay. And I thank for personal invitation for me for this talk and for this session, because actually I'm not a physicist, you know, but I dare to do some work which may be of some interest, to physicists. Well, I would like to speak of things which may be looking unusual somewhat, because there are functions which are defined on p-Adic numbers. There are functions which there are functions which are defined whose domain is real numbers or complex numbers. And normally, physicists, classical physics, they work with, so to say, continuous or locally continuous, something like this. Functions, they speak of, they work in Archimedean metric, and p-Adic metric is non-Archimedean, but we know that at least the world is, to say, Planck distances, or maybe not exactly Planck distances, but at quantum distances, the world is somewhat discrete. So my attempt is to somehow combine these two ideas, well, and to consider the functions which share two I'd rather say three main features. First of all, they are one Lipschitz maps. At the same time, they are continuous functions, continuous with respect to real metrics. So they are both Archimedean and non-Archimedean at the same time. I mean, speaking of continuity and etc., and other things like differentiability, etc. And they are causal. What are causal maps? They are. Now I will speak of causality and of causal maps, which are automata maps, which are p-Adic one Lipschitz maps, and which are at the same time continuous. Archimedean continuous functions. So this is the short outline of what I am speaking about, and I will start with things which may be not known to everybody, because at this conference there is no need to explain what is p-Adic numbers or what are complex or real numbers, etc. But to recall once again what is an automaton, or what is the system, a discrete system. It is, I think it is important. So it is this, the discrete system, or a system with discrete time, is formally speaking is this five tuple, which has well, a non-empty finite state, that the input alphabet, it get some letters, some symbols of as input, produces some symbols of output. So they are both these alphabets are finite. The system has a non-empty, possibly infinite set of epistemic states. I stress this word epistemic now because actually we cannot observe these states. We can make only some judgments about them. And what else? With it has a state transition function, and it has an output function. How it works? State transition function. If an automaton is a system in a certain state, when it obtains a certain input symbol, it changes its state and produces new symbol from the output alphabet. This output output symbol depends on the current state and on the input symbol. This is quite easy idea, very popular in computer science. This is a notion of an automaton. or a letter-to-letter transducer. It's the synonym. The system is called autonomous, whether its state update or state transition function or state or output function depend on inputs. So to produce something, not looking what is at the input. This is these autonomous systems. Other are called the non-autonomous. So you may use in look at so from that point of view of the system. So it has state, it has input which acts on a state update circuit which updates the input, and it produces output which depends on current state and on input symbol. It produces an output symbol. Okay, so how it works? This autonomous first input symbol at time 0, it produces the output symbol which depends on the initial state and the input and in first input symbol. Obtain the first input symbol, then updates its state. So the new state is that one. It produces the symbol, output symbol, which depends on this current state, which is a new one. It's already updated, and it depends also on input symbol number 1, and the next, etc. This the automaton determines the function, the mapping, which is called the automaton functions. It maps infinite words over the input alphabets to we may think of infinite words to the output alphabets this way. So this is the infinitely long or finite, it makes no difference currently, of infinite long of input alphabet and infinitely long word, corresponding word of the output alphabet. But note what happens. Every output symbol depends only on input symbols. It cannot it does not depend on symbols which were not inputted. In this meaning, we can speak that the system of causality, the causal system over discrete time. So this is a mathematical formalism of causality law. So input symbols may be judged as causes, output symbols as effects, etc. But what is interesting? So it is this mapping is completely determined by the sequence of these functions phi, right? And vice versa, if we have a sequence of these functions, know that each function depends only first the function number I depends on the on the symbols chi0, chi I. Yes, and every such sequence of function depends. This is discrete function, so it's have only discrete values, right? And every such sequence determines an automaton function. It maps infinite words to infinite words. But we can take that input alphabets, actually this is mostly a technical limitation, that both input alphabet and output alphabet consists of p symbols, and we can think that p is a prime. And this way we associate to input and output words which are infinite, the p-Adic integers. We can read this infinite string as a canonical expansion of a p-Adic number. So this map, we immediately defined the map, which is an automaton functions under T1 Lipschitz, and it one Lipschitz with respect to p-Adic metric because of this condition, and vice versa. So univariate one Lipschitz functions can be judged as univariate causal functions over discrete time. As functions describe a temporal evolution of a system under the sequence of certain impacts or causes, whatever you like. And what is interesting that it is if and only if condition. So every function, every one Lipschitz function, it defines an automaton in that meaning, exactly in that meaning. So speaking of automata functions, causal functions, and of one-Lipschitz functions, is the same. So we in more general model, if we have n symbol input or m symbol output with the same dependence, so the output, this columnar, rather say columnar vector, well, it depends only first columnar input vectors. And what happens inside, we don't know. It is a black box for us. We only can judge what happens, compare the input and the output. So if this n symbol input, so we can judge it as pn symbols of the alphabet p to the power n, and output every m symbol output may be judged as and a single symbol of p output of an alphabet which is p to the power n. That's all we can do. We don't know. We don't know what is inside. We only have a function. We only have a mapping, which we know is one-Lipschitz because it is causal and nothing more. And we can observe. We can compare inputs to outputs. Nothing more. And long, of course. This time series are long. And so this is the main idea. This is the main idea. We have a function which we don't exactly know what inside, but we expose it to some long series of impacts. And again, in this case, the causality also means one-Lipschitzes that because what is the output does not depend on what is not inputted yet. So it depends only on what had happened. Okay.
Can I ask?
Sorry?
Can I ask a question?
Yes, of course.
Yeah. Why do you call one-Lipschitz function the causal function?
Pardon?
Why do you call causal your one-Lipschitz function?
Just because of this property. Because the output symbol, every output symbol depends only on symbols which have inputted before this symbol was outputted. It does not, you see, we have a very long string, and every output symbol depends only, you see, do you see I here? So the output symbol number I depends only on symbols which were inputted at the time 0, time 1, time etc., time I. But it does not depend on symbol which is inputted in time I plus 1. Just does not.
Okay.
This is causality. This is causality. It's actually not my definition. It's well, standard definition of causal functions, but I will not.
So the point that it depends only on the previous.
Yes. The point is it depends only on the previous, nothing more. Well, all these states we are speaking, we can write states in many ways, but because every one-Lipschitz function depends on an automaton function in the meaning I just explained. It has states, some states. It has a state update function. It can be every one-Lipschitz functions can be described in that words rather than just as one-Lipschitz. So this is if and only if condition. And if it does not depend on the future inputs, this means causality. This means causality, nothing more. So the external observer can only make some guesses about internal structure of the system by observing pairs, causes and effects. So pairs X, Fx, if we have this map, which is one-Lipschitz map, and nothing more. But no, well, to every one-Lipschitz functions, we can put into the correspondence infinitely many different automata. So meaning they have different sets of epistemic states, different states of these transition functions, etc., etc. But this makes no difference. We deal only in these functions. I will later go to. Of course, we can choose them in some minimal manner, but a bit later I will show how it looks, so to say, graphically on a graph, but not now, because now I am speaking about rather function. But what is
Any
interesting?
automata is causal by definition, actually.
Sorry?
Any automata is causal by definition.
Yes, automaton is causal by definition, right? And one Lipschitz function is an automaton function, and every automaton function is one Lipschitz. So this is just synonyms, nothing more. It is one and the same thing. The class of all automata functions coincides with the class of one Lipschitz functions. That's all. At the same. And but what is interesting about these epistemic states? One Lipschitz map is called a finite automaton functions if there exists an automaton having of p this p to the n symbol input alphabet, p to the m symbol output alphabet, and if this function can be expressed as an automaton function which has a finite number of states. These automata are specific, somewhat specific. You will see that. Actually, we'll deal with functions which are not automata functions, but which are automata functions, but which are not finite automaton functions. For instance, that mapping x to x squared. This is an automaton function. That's just squaring, but it cannot be expressed, but it cannot be performed by can be performed by no finite automaton. It needs only infinite number of states to express this function. Okay, then we are continuing. So a real world physical system cannot have infinite number of states, but the number of states can be too large in comparison to the time elapsed or with the length of finite words or something like this. So we will use infinite automata because well, actually infinity is just a notion which helps us in our calculations. So I think that there are no things in a real world which you can say that is definitely infinite. They're just finite, but just the state, the number of something is very high compared to something, and this means that the automata with infinite number of states will be a good model for this situation. But something is very big, very large compared to the given quantity. Oh, okay. So examples of automata function: a constant automaton function. It is a finite automaton function if and only if it is constant, which is p-Adic integer and rational integers simultaneously. So what are these functions? What are these constants in terms of sequences? Because the constant functions well, means the automaton is well, it does not depend on input words, so it just produces a constant, and this constant is eventually periodic, so it is periodic from a certain moment. So these are that numbers exactly. Constant functions which are produced by finite automaton are just p-Adic rational p-Adic integers, so to say. And a fine map. A fine map, it's the map of these formulas. We are speaking now about one-dimensional, so to say, case. This is the map ax plus b, where a and b, x and b, but a and b, it corresponds to a finite automaton function if and only if that a and b are p-Adic rational numbers. A polynomial map. Well, if we take a polynomial whose coefficients are here, it is an automaton function. Every polynomial with p-Adic integer coefficients is an automaton function, but it is never a finite automaton function provided the degree of the automaton greater than 2. So only automata of degree 1 are finite automata, but polynomials, I mean, but we, of course, we will can consider polynomial in the talk. Remind that they are infinite automata. Okay, but note. So the first maybe important note. The maps define polynomials whose coefficients are rational p-Adic integers. So from here, these are first examples of our interest. These maps are automata functions. They are p-Adic one Lipschitz functions. They are continuous, and they are continuous real value functions. And both these functions agree on this set. Although these derivatives agree on this set as well. What does this mean? If you take a polynomial and which is defined only here, then as it is a polynomial, a continuous one Lipschitz function, because continuous because it is one Lipschitz, you can expand it to the whole set of p-Adic numbers. If the polynomial is defined only here, but because it is a polynomial, it is continuous, you can expand it to the whole real line. This is the idea. So these polynomials with coefficients from here, they live simultaneously in two worlds, in p-Adic and in real world, and they derivatives as well, because if you calculate derivatives of a polynomial, you will obtain again a polynomial, and of course it's again agree on this set. And the first question, of course, are there other functions other than polynomials, or in a similar way, which are not polynomials? There are, of course.
Excuse me. Polynomials on which variables?
You can judge it. You can judge it anyway. If you want to consider the polynomial is given as an expression of that ring. This is a ring. So you can input into that polynomial a p-Adic integer, and you obtain a p-Adic integer as a result. You can put into this polynomial, because coefficients are from here, you can input in this polynomial a rational integer from here, and you will get a rational integer from here. Then you just may continue it to real numbers or to p-Adic numbers. Then you just choose in what way you're working. If you're working with p-Adic numbers, well, input p-Adic variable. If you're working with real numbers, input real variable. No problem. But mind that they agree on this set.
Polynomial with respect to rationals.
Sorry?
What is where your variables, p-Adic or real?
They are simultaneously p-Adic and real, because
rationals variable.
But you can because polynomials are continuous, both with respect to p-Adic metric, and both with respect to real metric. You can expand it in two ways, both in real and p-Adic, and they will agree. And the derivative will agree on this set. This is the idea. They live in two worlds simultaneously.
No, I don't understand. Coefficients are integers, p-Adic integers, rationals, okay?
Yes.
But variables in your polynomials, p-Adic or real, or rationals? In polynomial coefficients, it are the variables.
Variables, you can take, you just decide what you like, where you will work. You will work. You say, I will look at this polynomial as a polynomial over reals. Okay, you can work with it as a polynomials over reals. You can take derivatives of these polynomials, for instance, and this will be okay. You say, no, I will work with this polynomial as a function over p-Adic integers. You also can do multiply, do like this, calculate, do everything you want. I mean, for example, take derivatives. But when you do this, if you input, for example, a variable from this set in the derivative, it will be, you will get the same value which will be from this set. You can treat it as real and as p-Adic. as you want. You see the
Polynomials over rational numbers. Is it true or not? Because I see here two polynomials. One is p-adic and another is real.
no, one polynomial. You can take here, for example, you can take here 1/3. This is a p-adic integer. Then the result be 1, 9. How you will judge these two numbers? I can judge it as a p-adic integer. I can judge it as real number. How you will judge this number? I can judge it as p-adic integer, to p-adic, of course, p2, for example, p2, we take p2. As two-adic integer, and you can judge it as two-adic integer and as real number. But they are the same, both from p-adic side, both from real side. They are the same. This is the same function.
But if you consider polynomial as a function from something to something,
I consider polynomials. Well, as this form.
A polynomial is nothing but a finite sequence of coefficients. It has
Right.
no variable.
Yes.
The variable is just a formality.
Yes.
To be able
Yes.
to use it as a function. So you have to distinguish between polynomial and polynomial function.
okay.
Yes. Nothing
I
more.
think I was confused. So polynomial is a sequence of coefficients.
Yes, and but it is important that this must be here. This must be here. This must be here.
But you promised in the beginning of the talk to present an example of a function which is continuous, periodic, and real norm.
This is continuous as periodic function, right? And this is continuous as real function, right? Squaring is continuous periodic function. Squaring is continuous real function.
Okay.
And the results of calculations, if you put as a value of a variable is from here, if you put here rational periodic integer, you obtain the same value. The same value. Never mind where you do calculations. You can do calculations in periodic numbers, you can do calculations in real numbers, but the result will be the same. If coefficients of polynomials are from here and variables are taken from here. But if you want further work with this polynomial over reals, you just expand it to the whole set of reals numbers because it is a continuous mapping. And this set is everywhere dense. The core point is it is everywhere dense, both here and both here. It is everywhere dense. It is dense in R, and it is dense both here and here. This is a dense subset, and it is sufficient to define a function only a dense subset if it is continuous. So I will just do it and nothing more.
Okay, if you consider polynomial as a set of coefficients, then it's all right.
Okay, so I can continue, yes?
Thank you.
Oh, thank you. Okay, so polynomials are this map. Well, what are these other myths? So we now consider given a prime p, we denote by CPR the class of functions which are continuous, continuous real functions, and with respect to metric, and which satisfy the with respect to real metric, which satisfy the following property: if the range, if the domain is p-adic rational numbers, then the range also must be within the p-adic rational numbers. So it maps these to here. There exists a p-adic one Lipschitz functions such that it also maps p-adic rational numbers to p-adic natural numbers, and it agree with these real function or for all that points from here. That's all. So it is continuous both here and here. So half of my time passed. Okay, so this is the main class we are focused on. So now we will not differ from between this function and this. Only I will say what we are doing. We are consider what domain we consider real or p-Adic. But the class is the same because they are all continuous. They're continuous as p-Adic functions. They're continuous as real functions, and they agree on this set. Nothing more. Okay, so polynomials are examples. And for example, given a polynomial of this, given two polynomials such that that polynomial is never zero modulo p for all p-Adic integers. So this is rational functions. This is a rational function also here. So you can do all calculations with these functions in real numbers, in p-Adic numbers. But when you do calculations taking the value of the variable from here, you will obtain the same thing, the same result, both in reals or in and in p-Adics. Nothing more. These rational functions are example of functions which are infinitely many times differentiable, and moreover, their derivatives also lie in this class. Their derivatives also share this property. They are continuous both as real functions and as p-Adic functions, and their values are the same. Their values agree on this domain. The first question. So we now know this by that symbol. The functions which are k times differentiable. K times differential makes no difference how they are differentiable with respect to what metric. They must be differentiable both with real metric and both with p-Adic metric, and the results must agree on this set. And C infinity is the subclass of these functions which are infinitely many times differentiable. So these functions are infinitely many times differentiable, of course. So the next question is, are there functions which are at least k times differentiable other than rational functions? Yes. And this question and answer has a prehistory. Once Weierstrass asked Hilbert whether there exists a smooth real function, which is not a rational function, but which maps rationals to rationals. The answer, well, the story said that the answer was positive, but neither records of the conversations nor Hilbert's example are known. Later in 1939, Green published a paper about functions of that sort, which maps rational to rationals, but are nevertheless not rational functions. So the fraction of two polynomials. And later, Markholm presented another examples of complex analytic function, or a holomorphic function, which maps rationals to rationals, and which is not a rational function. So each is not a ratio of two polynomials. So, but he was speaking only about rationals. This is, I can, well, rely on all these ideas. We can construct functions which are k times differentiable, but which are not rational functions. Few words about construction. So the said functions, the said examples are complex entire functions of this form. What are these Q? We take enumeration of all limits from here. We just enumerate it in any order because it is countable. It is a countable set, right? So we can enumerate them. Then we take these functions and then we take coefficients in some special form such that coefficient tends to 0 as p-Adic functions, as p-Adic integers, and is with respect to p-Adic metric and with respect to real metric as E tends to infinity. I again, because if there were questions, I again must say, well, here could be here could be some misunderstanding, because, for example, these functions, well, way to Pn, sorry, let it take -1. It periodically it is -1, right? Periodically it is -1, but as a rational function, as a real function, it tends to 0. And take another function, Pn to P to n -1. So this sequence, this tends to 0, this tends to 0, both here and here. This will be always 0, this sequence of numbers. And these numbers, of course, are from here. They are from here. Okay. Now, coefficients must be of that form, but they must satisfy some more complicated conditions, which I have no time to speak of. So this was looked from the real side. Now we will look from at these functions, from another side. Any one Lifshitz function, any one Lifshitz functions can be represented by a Muller interpolation series of that form. This is integral part of logarithm is if I is 0 is taken to be 0, and this is standard. This is standard thing. So we can consider functions, p-Adic functions now of these forms such that these C these all the coefficients are p-Adic integers, and they tend to 0, p-Adically tend to 0. And they constitute a subclass, a good subclass of p-Adic functions, which we denote by C. That's and there are another functions, a bigger class of functions, of that form, such that the bi here are p-Adic integers, but such that bi divided by I factorial is also in ZP. This is a good class of function, which is called B functions. It is called B functions. Why it is good? Why it is good? It is a complete with respect the first of all it is we can define the non-Archimedean metric on functions. This is just what sort of the metric? This is just we define p-Adic sup norm. We define p-Adic sup norm. And this is, in other terms, it's just p-Adic sup norm. It is so we just say that two functions, a distance between two functions is 1 to Pn if they are the same function modulo Pn, but there are different functions modulo Pn plus 1. We can because of this form of this function, because they are one Lifshitz, so the because they are one Lifshitz, and so they are all these functions are all these functions are all these functions well defined, so taken modulo P. Okay, and what is this more about this class of functions? This is closed with respect to additions, multiplications, derivations, infinitely differentiable functions, and composition of functions. And the polynomials with integer coefficient is dense in B. So every function can be uniformly, p-Adically, uniformly from this class can be uniformly approximated by polynomials with integer coefficients, which are, they are lying into class. So these functions are locally constants. They are locally constants of this form. All these derivatives. So you can you can write the Taylor series of this form, and all these derivative, all these coefficients are p-adic integers. What is interesting? This is a rich class of functions. It contains rational functions. It contains exponential functions. It contains p-adic trigonometric functions. It can contain p-adic logarithms. So it is a rich class of functions. The functions we constructed, what I talk about, which are both, which are constructed, which are both, this is example of functions which are not rational functions. They are exactly in this class B. This is the point of our interest. They are exactly of this form. Exactly of this. No, not exactly, of course. Not exactly. They are of this form, but it is an open question. It is an open question whether this fact implies that the function we constructed are infinitely differentiable. They are k-times differentiable. I can construct this, but not times. And now I can only ask the following question: what are functions which are infinitely many times differentiable which are both real and both real and p-adic in both situations? This is what I am going to ask. And now we continue. We continue with this in mind, and we only go to some properties of automata functions. So if you take a function, finite automaton function, which is from this our class of interest, from the class of our interest, and which is differentiable and as a real function or a real metric, and which is differentiable as p-adic function, and if its derivative is both continuous with respect to real metric and with respect to p-adic metric, and they coincide on ZQP by the definition of our class, then there is an affine function, nothing more. These functions correspond to automata with only finite number of states. This theorem is true in multidimensional case, and it may be treated so well. Why in quantum mechanics? Well, because in multidimensional case we will have an affine mapping. This will be a matrix, and this will be a vector. And why, if we have a system with a finite number of states, which is discrete states, which is differentiable, then this is necessarily affine. And another theorem, the so to say hologram-like property. If we have two functions of our interest, so from our class, which are both real and p-adic and continuous, and they're defined on the whole real line, as I said, and if they are the same function of some maybe small interval, arbitrarily small interval actually, and if they agree on these numbers or on this interval, they agree everywhere. So these are the same function. So know how the function this function behave on arbitrarily small integral. We know everything. It's so to say the all information encoded in the behavior on arbitrarily small interval of the function. This is like a hologram. We can take a small plate, a small piece of hologram plate, and restore the whole hologram. And then, this property can be used in order to construct various classes of automata functions which approximate real functions. We can take polynomials with integer coefficients, but I have many few times. I skip this classical results that we can approximate our functions which with polynomials of actually we can approximate them by functions with integer coefficients, usual integer coefficients, and we can do this. We can approximate them p-adically. We can approximate any functions because the functions from here are functions from that class, and the function from here can approximate any functions. If for example, Chlodowski theorem, which does not contain an integer, so it can be uniformly approximated by these polynomials, and we can even approximate it by polynomials, by functions which are represent reversible mappings, so they which are time reversible functions. These are reversible automata, and ergodic automata. Must skip all this. I must skip all this and go further. Okay. Why it is so? It is. It will be omitted. Oh, sorry. It is omitted. So any continuous real valid functions, the conclusion defined on real interval can be uniformly approximated by time reversible automata. So by time reversible causal function can then be treated as time reversibility at Planck time scale, but generally non-reversibility at macro scale, I don't know. But it is so. But it is so in this case. It can be uniformly approximated by ergodic automata functions. This is a short proof, which I have no time to expose. And this is why I am speaking about ergodicity. Ergodicity is like a clock. Ergodicity is like a clock. You may speak of, you may think of ergodic function, of the current, so to say, iterations of ergodic functions at the state of, a counter, so to say, which here are figures, like an electric count, like a electric power or counter or something like this. So they change. They change. Here they change the period of these changes p. This is p squared. This p cube. This pk plus 1, etc. And this goes to very interesting. This leads us to very interesting question. If we speak about chaoticity, then a well-known example of chaotic map, the logistic map, it is not chaotic at Planck's distances, not at all. It is not even ergodic, but it is not mixing. But it not even measure preserving, but not speaking, not ergodic, and so not mixing. But it is because all on one Lipschitz maps, they all have zero entropy. They all are all conjugate, ergodic, I mean, one Lipschitz maps. They are all conjugate to that odometer map, and thus all have zero entropy. Well, but it is a well-known chaotic map. Where does that come from? And now we must go to another thing. So we must expand our automata maps on a circle. So we will do this by using characters. We'll do this by using characters. We will do this by using character map of two types, real characters and p-adic characters. So if we have a function, which is integral of fractional, but of these are respectively, and we can expand by this way our function to the whole field, p-adic integers, and this is naturally can be treated as we time shift. We make a time shift. The beginning of observation was say several Planck times before. This is why we before we start our observation. So this must be taken into the account that actually it will be agree on the functions which are 0 at 0, but it makes no difference. The first important thing, so if we do such mapping, then we map our p-Adic integer on a circle, and the result is so this is this is fractional part of our function, and this is which is extended on the whole QP, and this is the result. So these are maps circle to circle. So the graph of these functions will be points of the torus. Will be points of the torus, and we can take all these points, sending all s, taking all s as arguments. We will obtain the points in the torus, and thus we obtain a plot. So it can keep records of evolution of the system, so to say. In a similar way, we can define a mapping using characters, real characters. So this will be mappings like that. So we take that from here and map this point on a circle to that point of a circle, mine here. So this agree, okay. And we obtain again points on the circle, and they agree. Actually, if we take a closure, we obtain pictures. It shows where the system finery occurs, how it works. We can have our automaton, which we have input string, output string, finite words. So we put 0 point input word, 0 point output word. This way we obtain a number of points in a torus, in a unit torus, and so we can speak because the mapping the set is closed. We take a closure. It is measurable with respect to Lebesgue measure, and so it's so to say the square or figure, and we can ask what is the square or figure. It is either the 0 or 1. This is the automata 0-1 law. This is what happens when we increase the length. Look here, what may happen. So these are looking good. The points are uniformly distributed. Then I'm increasing the number of the length of input words. This is still also okay. The length of input words is now 15. It's also looking still okay, but now it's getting, you can see something, right? And something is getting more pronounced. And what do we have? It's look like a winding of torus. It looks like a winding of torus. And at the very end, we will obtain a winding of a torus. And if this happens, if the measure is 0. And if the measure is 1, you will obtain, well, the blue screen, so to say. I will not do, we will not show the picture. These alternatives correspond to the cases when the plot is nowhere dense. In this case, the measure 0 means nowhere dense, and nowhere dense also in this case means that measure is 0. Of course, in general cases, not so. Nowhere dense subset can have well, a positive measure. And the second case is the plot corresponds to the whole surface of torus. And well, polynomials. So we can speak about polynomials in all dimensions of these mappings. And polynomials, I recall this. We take iterations, for example, of any other function. This will be a point on the torus, on the n-dimensional torus. And polynomial of measure 1 is have all polynomials of degree greater than 2 are 1 in all dimensions, and this is what is said. Recall that they are all our functions of our interest. And well, what is interesting, then the distribution of points in the unit hypercube tends to uniform. This is another way from chaos. The first wave, first from chaos, results from Bernoulli-like shifts in real case of mappings, and the second one, if we take some input and iterate it too many times, and the chaos emerges from the lack of knowledge of our input sequence, so to say, beginning of our input sequence, and this is the chaos of the second type. What I mean by saying how it is mixing. Now I will omit. Now I will speak about that lines, which you can see what this type of lines. If our functions, if c square, so it is 2 times differentiable and 2 times differentiable, and the second derivative is continuous, and if they are produced by a finite automaton, then this we will obtain a picture on the torus like that. This will be a picture like that. Well, this will be windings over torus. This will be windings over torus, and but maybe that's very few times. Okay, to every winding we may put into the correspondence this in cylindrical coordinates this expression, this parametric expression, and having this parametric expression, we can put into the correspondence to our function, to our winding, this function, the function of this sort. This is the complex. This is the complex valued functions. Y is a complex number. Sorry, real number. And this way we how we put into the correspondence to a finite automaton, or to the winding, which produces to the winding this function. And this is a diagram. Imagine that you enter here. If the first input symbol is 0, then you will occur in that automaton, and you will never get out of here, and because there are no errors from here. And if you are here, if the first input symbol is 1, that you will never get out of here. And this corresponds to the graph of this form, So you will have, so to say, 2 different windings of a torus with and probability to obtain each winding is 1 second. In general, if you have an automaton which ends, of this form, which ends which minimal automaton, you will obtain with different probabilities. You obtain these fractions, and if you have then you will get the probabilities of obtain the winding. So you can consider this integral. Actually, this is a distribution. It's a generalized function, and so you can calculate this integral if you know this psi, which are coefficients of the windings, and what are these coefficients? It was important to say. It is important to say what is this coefficient. The physical meaning of the coefficients a, b is which is a finite automaton function, is it rotates a times around a circle in the interior of the torus, and the b times around that axis. So this is a frequency. This is a frequency. This one is a frequency. Okay, and oops. Okay, but my time is over. Sorry. I had to stop because actually this is what will be in the case of that automaton, which I expressed. You will obtain with this function, and we can give assuming to every pass in the graph, assuming the probability of the pass, which is an integer, you will obtain this distribution. Then you using the theorem of while you obtain uncertainty principle in a usual way using Schwarz classes, and you can use all compositions. For example, this represents tensor product of automata, and actually that's all, because I need to finish on that because I have no time to speak of other things. So maybe a few words, concluding remarks. Causal maps are one Lipschitz maps. The latter maps are exactly the maps which are performed by synchronous automata over a p-symbol alphabet. This set is dense, both in real and rational numbers. So we can use both real analysis, complex analysis, p-Adic analysis, and automatic theory. Functions completely defined on the values that they can take on any arbitrary small integral. The class contains all polynomials, so any function can be approximated by functions from that class. Any functions real or p-Adic makes no difference with respect to different. So it is can deduce some basic results which belongs to standard mathematical formalism of quantum mechanics, and demonstrate that linearity of operators emerges from finiteness of epistemic states of a system. And mathematical proofs are based on the only physical assumption that physical world applying distances is discrete and causal. That's all. Thank you.
Okay. Okay, so thank you very much.